Greetings, class. Have you ever pondered the great scientific mystery of the microscopic world? Why do some atoms guard their electrons fiercely, holding them hostage like precious treasure, while others simply give them away freely at the slightest interaction? It is a microscopic tug-of-war that dictates the very nature of our universe. Today, we will study mechanisms and applications of atomic ionization energy. All right, here's our game plan for today as we play Atomic Detectives. We'll start with what ionization energy actually is, look at the three main factors affecting it, and then figure out how to interpret successive energies. After that, we'll dive into a case study on sodium, learn how to deduce elements in their groups, and wrap up with real-world applications and your exam summary. Let's get right into it. Section 1. What is ionization energy? Let's lay the foundation. Okay, so here is the golden rule. Ionization energy is, quite simply, the energy required to remove an electron from an atom. Picture a massive tug-of-war. You've got the positively charged nucleus pulling inward and the negatively charged electrons being pulled. But this energy, it's not a one-size-fits-all number. The strength of that atomic grip changes based on the atom's unique properties. So what exactly is messing with this attraction?
Here are the core details regarding this topic. Review them intently for their deemed crucial for your finals.
That brings us to Section 2, the three factors affecting energy. Let's meet our usual suspects. Suspect number 1 is nuclear charge. Now, the nucleus is packed with positively charged protons, right? And as you add more protons, the total nuclear charge naturally goes up. Think of the nucleus like a giant tractor beam pulling on those outer electrons. A higher charge means a much stronger attraction, which means you're going to need way more energy to rip an electron away. Take lithium, for example. It only has 3 protons, but fluorine, it has 9. So fluorine's extra protons act like a vastly superior tractor beam compared to lithium. So here's your key takeaway to jot down. Greater nuclear charge leads to stronger attraction, which absolutely equals a higher ionization energy.
These are the vital facts linked to this section. Study them thoroughly as they are vital for examination point of view.
All right, suspect number 2, distance from the nucleus. It's pretty intuitive, but the force of attraction between opposite charges drops off heavily as distance increases. So outer electrons that are placed further out just experience a weaker pull, meaning far less energy is required to remove them. Let's compare lithium to sodium. Lithium's outer electron is sitting right there in the second shell. Sodium's? It's way out in the third shell. Now, sure, sodium technically has more protons, but that outer electron is so incredibly far away that it's just much easier to snatch. It's exactly like a magnet. A magnet pulls a metal pin super fiercely close up, but move that pin across your desk, and the magnet barely even registers it. So your key idea here, greater distance from the nucleus means weaker attraction, and therefore lower ionization energy.
Listed are the main insights for the heading discussed. Note them specifically since they are highly relevant for exams.
Finally, our third suspect, the shielding effect. Now remember, all electrons are negatively charged, which means they literally constantly repel each other. The inner shell electrons essentially act like bouncers at an exclusive club. They crowd the space and actively block the outer electrons from feeling the full attractive force of the VIP nucleus. We call this blocking action the shielding effect. As you add more inner electron shells, well, you're hiring more bouncers. The shielding increases, the attraction plummets, and that outer electron is just left out on the curb, incredibly easy to remove. Look at sodium again with its 2-8-1 configuration. That single outer electron has 10 inner electrons standing between it and the nucleus. So the key idea to locking for the exam, more shielding equals weaker attraction, which means lower ionization energy.
The following are critical points regarding this heading. Please examine them closely as they are highly significant from an examination perspective.
So let's quickly review the rap sheet for our 3 suspects. Increased nuclear charge, that increases the energy required, but increased distance and increased shielding, they both decrease the ionization energy. Make sure you etch this into your memory, guys. It's an absolute master key for acing your exams. Moving on to Section 3. Interpreting successive ionization energies. Time for some detective work. In the lab, scientists aren't just guessing. They literally interrogate atoms by removing electrons one at a single time from gaseous atoms, and they carefully measure the exact energy required for each consecutive removal. We call these successive ionization energies. Honestly, it's almost like hooking the atom up to a lie detector test. Reading the spikes in energy gives us hard, undeniable evidence about exactly how those electrons are arranged. Small, incremental increases in energy, that just tells us we're pulling electrons from the exact same shell. But large, massive jumps, boom, that tells us we've broken into a brand new shell that is significantly closer to the nucleus. Let's put this into practice in Section 4, Sodium, an atomic case study. Let's analyze the evidence. Okay, so sodium has 11 electrons total, structured as 2, 8, 1. When we look at the lab data for removing the very first electron, the energy required is surprisingly low. This is our first major clue. It proves that this specific electron is far away, heavily shielded by those bouncers we talked about, and frankly, it's given up without much of a fight. But watch what happens next. When we try to remove the second electron, there's an absolutely massive spike in the energy required. The atom is suddenly holding that second electron hostage. This huge jump is definitive proof that the second electron is in a completely different, much closer shell. It confirms unequivocally that sodium has exactly one outer shell electron. Let's keep digging into this data. As we continue to rip away the second all the way down to the 9th electron, the energy required definitely increases. But it's just a gradual climb. There are no sudden massive spikes. This gradual climb tells us that all 8 of these electrons reside in the exact same shell, sharing similar distances and attractive forces. But then, right between the 9th and the 10th electron, bam, another massive energy jump. This is the smoking gun that indicates we've hit the innermost shell, right up next to the nucleus. The attraction here is overwhelmingly strong, confirming that those final 2 electrons sit in that highly guarded first shell. Section 5, Deducing Elements and Groups, Cracking the Case. So looking back at our sodium data, we had 1 easy removal, 8 gradual increases, and 2 held extremely tight. Read that backward from the center out and you get 2, 8, 1. Perfect match to its known structure. But here is the absolute most powerful application of this data, using it to identify an unknown elements group on the periodic table. The method is incredibly simple but absolutely critical. All you do is scan the data to locate the very first large jump in energy. Then just count how many electrons were removed before that jump. That number exactly equals the total outer shell electrons. For instance, if you're looking at a chart and see a huge jump between the 6th and 7th electron removals, that means 6 electrons were sitting in the outer shell. And an atom with 6 outer electrons, that places it squarely in group 16. It's like a cheat code for the periodic table. And finally, Section 6, Applications and Exam Summary. Time for the final briefing. Now, you might be wondering, why do we care so much? Well, because this isn't just whiteboard theory. Understanding ionization energy is literally the bedrock of predicting chemical reactivity. It explains the entire architecture of the periodic table. By reading these energy signatures, scientists can identify completely unknown elements purely from a pile of experimental data. It's the exact knowledge that material scientists use to invent revolutionary new materials with bespoke chemical properties for our industries and technology. It beautifully proves that these invisible, microscopic forces of attraction dictate the massive, macro-level real-world phenomena that we interact with every single day. All right, class, I need you to take out your pens. This is your zero-emission checklist for the exam, so listen up. You have to master these core rules. First, ionization energy relies entirely on nuclear charge, distance, and shielding. Remember the directions. Greater nuclear charge drives the energy up, while greater distance and greater inner shell shielding drive it down. Second, successive energies allow you to map the entire atom. Small energy increases mean you're pulling from the same shell. Large jumps mean you've breached a new, deeper electron shell. And for part 2 of your exam summary, the data analysis. When you're sitting in that exam hall, the large jumps are the ultimate key to unlocking the question. Finding the exact number of electrons removed before the very first large jump is the most critical step you can take. Why? Because that number exactly equals the total number of outer shell electrons, which instantly hands you the elements group on the periodic table. 1 electron before the jump, you're looking at group 1. 6 before the jump, it's group 16. If you master these data interpretation rules, you can successfully analyze literally any unknown element they throw your way. And so, we reach the end of today's explainer. Think about everything we've just uncovered together. We've mapped the exact push and pull of the atomic universe. So I'm going to leave you with this. If a brand new element was discovered tomorrow, say crash-landed from a meteor and hidden deep in the earth, could you sit down in the lab and crack its atomic code just by interrogating its ionization energies? Armed with today's knowledge, I absolutely believe you could. Class dismissed.
Important terminology for this topic is shown on the screen, arranged according to various exam boards. These terms demand focused attention during revision as they are highly significant and must never be overlooked. Furthermore, a past paper evaluation is included for each board and paper format. Give this paper attention too, since it will strongly enhance and refine your preparation. Additionally, aims to grasp the meaning and usage of every term instead of rote learning them individually. Consistent practice of these terms in past paper questions will greatly boost your precision and overall exam results.
Please subscribe our channel to get more educational videos. Thank you.